Okay, welcome back. So last class we talked about how to solve sparse triangular systems in parallel. And the method that we talked about is called level scheduling. And today I want to talk about a very different method for solving sparse triangular systems. And this method is called partitioned inverses. It is a method that has a lot of very interesting ideas. It was developed in around the early 1990s. But before I describe the method, we need a little bit of background so that you can understand the method. And let me start by talking about the structure of the inverse of a matrix, meaning given a sparse matrix, how do we know what the sparsity pattern of the inverse, what does that look like? And generally, in many cases, the inverse will be dense, but in other cases, the inverse will also be sparse. Okay, so the interesting case is when the inverse is also sparse. So structure of the inverse of a matrix. Maybe I should say a sparse matrix. Okay, so given a non-symmetric matrix A, and I'm going to talk about non-symmetric matrices in this lecture because we're talking about triangular solutions, so triangular matrices are obviously non-symmetric. And its graph G, and remember G is composed of a set of vertices and a set of edges, right? And when Aij is not equal to 0, okay, then we have an edge from J to I in the set of edges E. Okay? So this is a directed edge. And this is the same notation that I used last class as well. And if we have a lower triangular matrix, then all of the arrows go from a low number to a high number. Okay, so J is less than I in a lower triangular matrix. And I'm also going to say I is not equal to J because I'm going to ignore the diagonal. Okay. Then what we're interested in is the structure of A inverse. Then the structure, meaning the sparsity pattern, has a graph as well. Okay. We call it G star. And this graph is the transitive closure. I'll explain that in a moment. Of the graph G. Okay, so let me explain what the transitive closure is. If there is a directed path let's say from J to I, okay, so this squiggly line means that there's a path from vertex J to vertex I, right? It's not necessarily an edge, but there's a directed path. From J to I in G, which is the graph of A, then in the transitive closure, there is an edge from G to I. I shouldn't say G, I should say J. I think G is the French pronunciation of J. So j to I, that's what I mean. Okay, j to I. Then j to I is in G star. So if we have a matrix with this property, then we call G star the transitive closure of G. Okay, so let's see an example of this. So here's a 4x4 example. Okay, 4x4 example, and it has a graph. So let's label the rows and columns. 1, 2, 3, 4. So these are the vertices. And there is a edge from 1 to 2, and an edge from 1 to 3, and an edge from 2 to 4. Okay? So what does the graph of, so this is G. What does the graph G star, the transitive closure, look like? Okay, we have a path from 1 to 4 in this graph, right? That means in the transitive closure, there will be an edge from 1 to 4. So I'm going to draw in red chalk an extra edge. And all of these white edges are also part of the transitive closure. So the transitive closure has an extra edge, which is this red edge. Okay? And the transitive closure has an extra, that means it has an extra non-zero here from 1 to 4. Okay, so you can try this out, let's say in MATLAB. Just give it this matrix, give it some values. Okay, the matrix, the original matrix with the white x's, and then compute its inverse. And you'll see that the inverse is also sparse, and it has an additional zero, non-zero over here. Okay, so this is a way of determining what the sparsity pattern of the inverse looks like. And you can also see that this argument is consistent with the fact that the inverse of a triangular matrix is also triangular. Okay, that's because in a triangular matrix, all of the arrows point from low numbers. Let's say a lower triangular matrix. All of the arrows point from a low number to a high number, right? And if we form the transitive closure, all of the arrows will still point from all of the low numbers to high numbers, which is a lower triangular matrix. Okay? Do you want another example, or is this pretty clear? I think it's pretty clear. Okay. All right, so this is the first thing to know, the structure of the inverse of a sparse matrix. The next thing to know is the representation of a lower triangular matrix as a product of elementary elimination matrices. And this you may have learned if you've studied Gaussian elimination. Let's say a unit lower triangular, meaning a lower triangular matrix with all ones on the diagonal. So given a unit lower triangular matrix, we want to represent it as a product of a set of matrices called elementary elimination matrices. So given a matrix L, which is n by n, lower triangular, So L can be represented as this product, L1 times L2 times L3 all the way up to Ln, where these L's, Li's are lower triangular and have a specific form. So an Li has this form that is all ones on the diagonal. And it has some values on the ith column below the diagonal. So this is the ith column of Li. Okay, and in Gaussian elimination, these are just the multipliers that are used to transform a matrix into upper triangular form. And all these multipliers fall below this diagonal. And you keep on accumulating these for each row that is eliminated, right? So this fact you may have learned before, that this lower triangular matrix can be represented this way. Okay, so here's an example. Well, actually, so here's a not just an example, but an important property. And I'll show it through an example. So suppose that we have this lower triangular matrix, unit lower triangular matrix, a 4 by 4, 2, 3, 4 in the first column, 5, 6 in the second column, 7 in the third column. Okay, so this can be written as the product of what? It can be written as the product of 4 lower triangular matrices. The last one is actually going to be trivial, so I'm not going to draw it. And it has 2, 3, 4 in the first column, 5, 6 in the second column, and 7 in the third column. Okay, so if you haven't seen this, this is pretty amazing. Right? So you multiply these matrices together, and the result is the union, in some sense, of all of these elementary elimination matrices. So you see the 2, 3, 4, 5, 6, 7, we just union, or we just glue them together, and we get the product. Okay? So we get this kind of union. However, the order is very important. Meaning, if we try to multiply this one times this one and times this one in that order, then we don't get this result. Okay, so we have to multiply it in this order, basically in increasing I. Okay, and you can see this actually fairly easily, because this matrix can be written as the identity plus, let's say, M1 times E1 transpose. So M1 is a vector that is this vector, but 0 in the first component, right? So M1 is just 0, 2, 3, 4. And E1 is just the coordinate vector in the first direction, right? So this is the identity plus this part. And similarly, the second term is identity plus M2 E2 transpose. Okay, so and M2 is 0, 0, 5, 6. Okay, and then there's a third term. I won't need to draw it. And if you multiply this out, you get identity plus M1 E1 transpose plus M2 E2 transpose plus M1 E1 transpose M2 E2 transpose. Okay, so here's the identity of the result. And M1 E1 transpose is that first column. M2 E2 transpose is the second column. And this product is actually 0 because E1 transpose times M2 is 0 because E1 transpose times M2 is the first component of M2, but the first component of M2 is 0. Okay. Now, if you try to multiply this in reverse order, then you'll see that you're going to get a term that is M2 E2 transpose times M1 E1 transpose. We could maybe write that in reverse. We would have M2 E2 transpose M1 E1 transpose. So then we have this scalar E2 transpose M1, but the second component of M1 might not be 0. So then this term might not be 0. Okay, so this is why the order is important. But actually, an interesting thing is that if the second component of M1 is 0, then this term is 0, and we get the same result as if we had multiplied in the reverse order. So if this term is 0, then the two factors can commute. And this is a point that we're going to talk about later on as well. So let me write that down. In general, if mi, which is the ith column, and the I plus first element of that column is 0, then Li and Li plus 1 commute. This element is just the subdiagonal element. So if we looked at some matrix, right, it's the ith plus I plus first element, I comma I plus first element, right? It's just a subdiagonal element. So if we have any subdiagonal elements, then we can commute. For this example, there are no 0 subdiagonal elements. That's a subdiagonal element in the matrix. So here's a second important property. So elementary elimination matrices have two important properties. Here's a second important property, which you, again, may remember. And that is, I'll show it through an example. Let's suppose that we have this 4x4 example. The inverse of an elementary elimination matrix also has very simple form. We just negate the multipliers. Okay? Okay, so with this background, we're able to now talk about partition inverses. And here's a reference that you can use. So partition inverses were invented by a professor at Wisconsin. I think he's now retired, Alvarado. And later on, he worked with a number of people to develop and prove properties of algorithms for computing these partition inverses. So Rob Schreiber and Alex Pothen. And they have a paper in 1993 that you can use as reference for what I'm going to describe. So their paper is called Highly Parallel Sparse Triangular Solution. And these days, when computers are getting more and more parallel and triangular solutions also being very important, as you saw, they were this important component of incomplete factorization preconditioners or preconditioning. Methods like this are starting to regain interest. Okay? So again, we are taking our matrix L that we want to solve with. We want to solve with this matrix L. And we're going to try to represent the matrix L as a product of sparse factors. And if we can, represent the inverse of L as a product of sparse factors. And if we can do that, then instead of solving with L, we just need to multiply with these sparse factors. You'll see this in a moment. So L1 is L. So L is equal to the product of L1, L2, up to Ln. Okay. So L1, L inverse is equal to Ln inverse, Ln minus 1 inverse, L2 inverse, L1 inverse. Okay. And in particular, if we want to solve, which is like multiplying by the inverse, solve with a system with the right-hand side vector b, Ln inverse, L2 inverse, L1 inverse b. Okay, so the naive idea would be to just write L as a product of these elementary elimination matrices. Right? And if we want to solve with B, then we're just going to multiply with each one of these elementary elimination matrices. And the inverses are easy to compute, right? Because the inverses they look like this. So we multiply B by L1 inverse, then the result by L2 inverse, etc. Okay? But this involves n matrix multiplies. And in particular, you can think of there being n steps, right? So before, we had a number of steps that was equal to the number of levels, right? But here we have n steps. So we haven't done anything fancy yet, okay? But you can see that this idea could be attractive, right? Because if we have a sparse L, right, and the L that comes from these incomplete factorizations are also sparse. If we have a sparse L, right, the inverse of L could be the lower triangular part of a full matrix, okay? But these individual elementary elimination matrices are sparse, right? So if we had some sparsity over here, 0, 0, these elementary elimination matrices are sparse. And in fact, the number of non-zeros in all of these elementary elimination matrices is equal, except for the diagonal, equal to the number of non-zeros in the original L. Okay? So multiplying this way can, that reduces the number of flops. Okay? Number of flops reduced. But the problem is that we have these n steps still. Okay, so the idea is, well, how can we reduce the number of steps? And the idea of Alvarado is that we're going to try to find some partitions. I'm going to write it like this. So find some partitions. So L inverse, I'm going to write that, but now with partitions, Ln inverse times Ln minus 1 all the way to, let's say, L2 K inverse. Okay, so this is possibly one partition. I'm going to call that PM inverse. And then a whole bunch of other partitions, maybe LK all the way to L1, all inverse. And maybe this is called P1 inverse for the first partition. Okay? So I'm writing exactly the same thing as this, but now I'm grouping some of the factors together. Okay? I'm grouping some of the factors together such that I'm going to have M groups. So PM, M groups. We used to have N factors, but I'm going to group them into M groups. And the idea is to try to find a grouping such that these inverses of P are also sparse. Okay, so that might not seem it's possible, but I'll show you in a moment how that is possible. And now when we want to solve with B, involving the vector B, instead of having n matrix multiplies, now we only have n matrix multiplies because we have m steps. So now we have m matrix multiplies. So we have m steps, and the goal is hopefully to find m that is lower than the number of levels we might need in level scheduling. Okay, if we can do that, then we have a method that is better than level scheduling. So we want to find these partitions such that the PI inverses are sparse. Okay. So maybe I should recall L is sparse. Right? So L doesn't have to be sparse for all of this to hold, but we have a sparse problem. This is the goal is for sparse triangular solves. A common more specific criteria is to say that we want to have a PI inverse with the same number of non-zeros, and in fact the same sparsity pattern as PI. Okay? We say that PI is a no-fill partition. So no-fill, similarly like incomplete factorization, zero fill, whatever. But this has nothing to do with incomplete factorizations. So PI is a no-fill partition if PI inverse has the same sparsity pattern as PI. Okay. So can this be done? Well, not always. It's going to depend on your sparse matrix, right? And in the worst case, you can just choose all of the partitions to be a single factor. So that will always work, right? So can always find trivial partitions where Pi is equal to Li. Yeah, Pi is equal to Li. Okay, so we're going to suppose that we wanted to find an algorithm to do this. And we want to find partitions such that Pi and Pi inverse have the same sparsity pattern. So how do we do that? So we saw just a moment ago some results based on transitive closure of what the inverse of what the sparsity pattern of an inverse looks like, right? So Pi has a graph, right? And we can find the transitive closure of that graph to find what Pi inverse looks like. And if Pi and the transitive closure of Pi, so I'm going to say transitive closure of a matrix, but I mean transitive closure of the graph of the graph of that matrix. So if we find the transitive closure, and if those two things are the same, then the inverse will not introduce any additional non-zeros. Okay? In some of the research that has been done, some additional non-zeros could be allowed. Those algorithms tend to be a little bit more complicated or messier. But the simplest case is to say, let's try to choose a partition such that each partition Pi doesn't introduce any fill-in in the inverse. Okay? So we'll see this in a moment. There's a greedy algorithm that can be used to find these partitions. So let's do this example. It's a 12 by 12 example. I'm going to draw a by 12 matrix. Okay, and I'm going to draw some lines to help me out. And it's going to be a lower triangular matrix with a full diagonal. So I'll first draw in the diagonal. Okay. And there's a non-zero at 2, 1, a non-zero at 5, 3, and 5, 4, and a non-zero at 6, 4. There's a non-zero at 11, 2, and a non-zero at 11, 5, and a non-zero at 12, 6, and a non-zero at 9, 7, and at 9, 8, and 10, 7, and 10, 8. And the last non-zero is at 11, 10. So we can draw the graph of this matrix. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And here are the arrows. And you'll notice that all the arrows point from the lower number to the upper number because we're a lower triangular matrix. And I'm kind of drawing the arrows so that if you see any mistakes in the matrix, you can tell me. But we'll use this graph a little bit later on. Okay, so this is the example we're going to use. And we're going to try to find the partitions for this problem using a greedy algorithm. Okay? And the greedy algorithm says I'm just going to go from left to right, okay, from I equals 1 to the number of columns that I have. And I'm just going to say, can I group the first two? Well, actually, it's going to be backwards in the inverse. So I'm going to say, can I group the first two? And yes, if yes, then I group them. Then can I group the next three? And if yes, I can group them. If I say no, then I'll stop, and I'll begin a new partition. Okay? Then if I say no for the first one, then I say, can I group the second and the third? Okay? So the first question is, for this one, can I group the first two? If I group the first two, we could try to write down L1 and L2, write down their inverses, L2 inverse times L1 inverse, and we want to know if any additional non-zeros are created if we do that product. And the easy way to do it is to use the transitive closure. Okay? So let's say, can we combine 1 and 2? Okay, so let's draw the portion of this graph that involves 1 and 2. Okay, so we only want to look at the first two columns, right? So the idea is to only look at columns 1 and 2, right? Because we're looking at the elementary elimination matrices corresponding to L1 and L2. Those only have these first two columns, right? So in the first column, we have this non-zero going from 1 to 2. Okay, and in the second column, we have a non-zero over here going from 2 to 11. Okay, so this is the part of the matrix, part of the graph that we're interested in if we want to know if we can combine 1 and 2 into a partition. So what does the inverse look like? So we formed the transitive closure of this graph. And in the transitive closure, because there are two edges, there's a 1 to 2 and a 2 to 11, in the transitive closure there will be an edge from 1 to 11. So the inverse will have this edge from 1 to 11 that is not in our L1 and L2. So the answer is no. We cannot combine 1 and 2. So no, cannot combine 1 and 2. So 1 has to be its own partition. So 1 will have to be its own partition. Okay, so now in our greedy algorithm, we'll say, well, can we combine 2 and 3? Okay, so we look in columns 2 and 3. And 2 has an edge pointing to 11. And 3 has an edge pointing to 5. Okay, so take the transitive closure. And in the transitive closure, we don't add any new edges. Okay, so the answer is yes. We can combine 2 and 3. Because if we take L2 and L3, multiply them together, take its, and then look at its inverse, it has exactly the same sparsity pattern as L2 times L3. Okay? Then we can ask in our greedy algorithm, can we add 4? Okay, in 4, we have an edge, so 4 goes to 5 and 6. Okay, so I've added 4. It has an arrow going to 5 and an arrow going to 6. So what do you think? Can we combine 4 with 2 and 3? So you have to look at the graph and say, well, are there any paths in this graph that are longer than one edge, than one step? Because if that aren't already in the path. So I think the answer is no. So the answer to that is no. So the answer to can we add 4 is yes. Okay? So can we add 4 is yes. And how about 5? Can we add 5? So 5 has an edge to 11. 5 is already here. So I'm going to add this little arrow from 5 to 11. And how about now? What does a transitive closure look like? Does a transitive closure involve adding any additional edges? Yeah. So there's a path from 3, 5, 11. That means we would have to add an edge 3 to 11 in the inverse, for the inverse. So fill is created. So the answer to this one is no. So we can't add 5. We can't add 5. So we're done with this partition. This partition involved 2, 3, 4, and 5 is going to be a new partition. All right, so maybe we should do a couple more steps. Can we combine 5 and 6? Yes. Okay, I think that's correct. I found also we can combine 5 and 6 because 5 and 6 has 5 pointing to 11, 6 pointing to 12. So yes. Can we also combine 7? Yes, because 7 has an arrow pointing to 10, and 10 has an arrow pointing to, no, so 7, 10, and 7 has an arrow pointing to 9. Seven, 10, 7, 9. 7, 10, 7, 9. So 7 is also fine, right? And how about 8? So 8 has points to 9 and 10. That's also okay. And how about 9? 9 has arrows from 7 and 8. So that's already actually done. So in fact, 9 probably no additional edges need to be added. And how about 10? So 10 is a no. So let me draw that one in blue. So 10 says we're going to need to add an edge to 11 from 10. And you can see that once we do this, there's a path from 8, 10, 11, and there's no edge from 8 to 11. Okay, so that's a no. So if you carry out this process, you'll find that the partitions are P1 by itself, or maybe I should call it L1 by itself. Yeah, so that's L1 by itself. And then L2, L3, L4 is one partition. L5 up to L, what did we say? L9. And then L10, L11, and L12. We didn't do this on the board, but you can also verify that they are their own partition. Okay, so 5 steps. So 5 multiplies. So this was a very sparse example. It would be more interesting to apply it to some examples that come from, let's say, PDE discretizations. And let's just take the simplest one, like discretization on a one-dimensional problem, which leads to a tridiagonal matrix, and the lower triangular part of a tridiagonal matrix is just a bidiagonal matrix. Okay, and let's say we have a bidiagonal matrix. How many partitions do you think we will need? So let me draw this example. So maybe I'll draw the matrix. Okay, so the lower triangular part of a tridiagonal matrix is this bidiagonal matrix, and the graph looks like this. Right? So if we number the rows and columns, we get this numbering, and here are the arrows. Okay, and what do you think? What are the partitions? So you may start to get good at looking at what the partitions are because you saw this graph, right? So can we combine 1 and 2? Can we combine 1 and 2? So what is the graph of 1 and 2? So we have 1 pointing to 2, and 2 points to 3, right? But there's no 1 to 3, so that would be Philion. So we cannot combine 1 and 2. Okay. Can we combine 2 and 3? by the very same argument, we cannot combine 2 and 3. And so we cannot combine any. So for this example, all of the partitions are the trivial partitions. Okay? Unfortunately, this is a very common case. So it seems like this method really sucks. Similarly, we can let's look at a mesh. Right, so number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? And the size of this matrix is 16 by 16, right? Some of you actually got this, well, probably a little bit confused in the exercise a couple days ago, in which we also did a 4 by 4 mesh, but then you drew a 4 by 4 matrix. The matrix is 16 by 16, okay? And we can draw the arrows. Let's consider the lower triangular matrix in this ordering. So we could draw the arrows. All the arrows point down and across. And in the first 1, 2, 3, 4, this looks just like this one. So there's nothing to combine. Are there any partitions that can be combined? So 4 and 5 can be combined. Okay. How about 4, 5, and 6? No, 4, 5, 6 doesn't work. And similarly, 8 and 9 can be combined, and 12 and 13 can be combined. So we can combine some, but there's not a lot that can be combined. Okay. If we were somehow able to change the ordering of the problem, if we can change the ordering of the problem, that could change the partitions that we can find. Okay? So if somehow we go back to looking at our AX equals to B problem, and we reorder that matrix, then we come up with, let's say, a no-fill ILU factorization, and then we look at the pattern of the numbering. Let's see what happens in that case. So suppose we take the same problem over here and we reorder it Okay, so to be very clear, this is a one-dimensional problem, and I'm not drawing the arrows because this is just the symmetric matrix. This is just the discretization, the finite difference matrix. Okay? And now let's reorder that matrix. Reorder just means renumbering the vertices. Okay, so we'll reorder the matrix. Let's say we'll pick 1, 3, 2, and 4. Okay. Then we compute the incomplete factorization with 0 fill. So no additional edges are added. And then we're going to look, and let's look at the lower triangular factor. So if we're looking at the lower triangular factor, that matrix is non-symmetric. We have to add some arrows. And all the arrows go from low to high because we're going to look at the lower triangular matrix. So low to high, low to high, low to high. Okay, so this is our new lower triangular matrix. Let's draw this matrix to see how it compares to this matrix. So there's the diagonal. And there's an edge from 1 to 3. and an edge from 2 to 3, and an edge from 2 to 4. Okay? And now we're going to say, well, what are the partitions? Okay? Can we combine 1 and 2? So combine 1 and 2. So there's this graph for 1 and 2. We have 1 pointing to 3 and 2 pointing to 3. Maybe I'll draw 2 over here. 2 pointing to 3, and also 2 pointing to 4. Okay, in fact, it's the same as this. Not surprising. And this is the same as its transitive closure. So there are no new things that can be added, no new edges. So the answer is combine 2 and 3, that's yes. Can we also combine 3? If we combine 3, look in column 3, there's no new edges that I need to add. So the graph is the same. So the answer is yes. And can we combine 4? The answer is also yes. So pretty amazing. We just reordered this a little bit. And now the inverse of this has exactly the same structure as the original matrix. So there's no fill-in in the inverse. Be careful, we're taking this and we're computing an incomplete factorization. So this is the pattern of the incomplete factorization, not the complete factorization. The complete factorization will have fill-in, and then you can't do this. So, but in any case, if you're trying to solve with these incomplete factors, this reordering in this example really made a big difference, right? So we can combine all the Li into a single partition. And in this particular case, it means that the inverse has exactly the same pattern. Any questions so far? So how well this works kind of depends on what ordering to use. It's a little bit like level scheduling, right? If we use multicoloring, we really reduce the number of levels. And here, this looks a little bit like a multicolor reordering that I chose, and it reduced the number of partitions. In general, there's something else that you can do, and it's related to commuting the Li and the Li plus 1. Okay, so here in our greedy algorithm, we looked at all of the L's in sequence, and we said, can we combine them? Right? But some of these L's can be swapped. If Li, comma, I plus 1 is 0, then the two factors commute and we can swap them. And if we take that into account, maybe we can find better partitions. Okay, so there's another way that we can maybe find some better partitions. And in general, it means that we can try to find a reordering of the triangular matrix, a symmetric reordering of the triangular matrix that is also triangular, and apply the partitioning algorithm to that. Okay, so let's write that down. So what I've shown you first is just this greedy algorithm for finding the partitions by maintaining this strict order of I, from left to right. And now let's look at what we could do if we consider some permutations. So I want to keep these two things on the board. So I'm going to erase this part. And in fact, I think I want to save this part of the board, so I'm going to erase this part. So recall, just from earlier in the lecture, we can sometimes swap Li and Li plus 1 if, now my notation is going to be a little bit weird because here the subscripts represent the subscripts for the elementary factors or the elementary elimination matrices. If, let's say, my global L, I plus 1 is equal to 0. Okay, so this is an index into the original matrix L. And it's a little bit hard to believe. I kind of showed you how it works on the board, but if you have trouble believing it, you can just construct an example like this and try it out. So in general, we can try to permute or reorder L into QL Q transpose, where Q is a permutation matrix. Okay. Let's call that LQ, such that LQ is triangular. So generally, if you have a dense triangular matrix, there's no real way to reorder it so that it's still triangular. But if the matrix is sparse, then you may be able to find such a permutation. Okay, you can't always find it. Okay, but for some problems, you may be able to find such a permutation. And let's try to find such a permutation for this graph. Okay, in other words, we have a structure, but we don't know the numbering. Okay, so I'm going to redraw the structure, but I'm not going to draw the numbers, because the new numbers is going to be the new ordering. So here we have the structure. The edges have to stay the same. Okay. So we want to find a new numbering such that the matrix is still triangular. Find a numbering such that the matrix is triangular. Let's say lower triangular. If we mean lower triangular, that means we're going to have edges that go from a lower number to a higher number. Okay, so we want to find a numbering from 1 to 12 such that all the arrows point from a lower number to a higher number. Okay? If you look at this example, All of the arrows point from a lower number to a higher number. But the numbering is not unique. I mean, there's not only one numbering that will, for which this will be satisfied. You can find another numbering, okay, such that this is lower triangular. And in particular, you want to find a numbering such that you might be able to improve, meaning reduce the number of partitions you need in this partition inverse method. Okay, you would really want to reduce the number of partitions. Just like over here, we had 4 partitions, and then we were able to do 1 partition. But this was reordering the matrix. This is kind of related, but we're now reordering the lower triangular factor. Cannot always be done, okay? Because if you have a specific structure here, you may or may not be able to do it. But in this case, you can. Okay, so which one should we number 1, let's say? There's more than one good choice for number 1, right? We could choose this to be number 1. That may or may not be a good choice. Is it a good choice or a bad choice? It's not a good choice. So why isn't it a good choice? Because at some point, this has to be numbered, and it will be numbered greater than 1. And then we have an arrow that goes from a greater number to a lower number, which violates this, so the matrix will no longer be triangular. Okay, so this is not a good choice for number 1 because there's an arrow pointing into it. So we would like to choose a node that has no arrows pointing into it as number 1. And in general, we can have this concept of a depth of a node. And the depth of a node is the length of the longest path, longest directed path into that node. Okay, so a node like this, which has no paths into it, has a depth of 0. Okay, and a node like this, which has a path, the longest path into it, this has a depth of 1, and this node has a depth of 2. Okay? So the depth of a node, we'll define that as the length of the longest directed path. Put directed in brackets because it should be taken for granted. Directed path into a node. Into a node. And we could write down what all of the depths are for these nodes. Right? So this one is 1, this one is 1, this one is 1, this one is 1, this one is 1. And now we can find all the 2's. This is a 2, this is a 2, 2. Wait a minute. I should not have called those 1s. I should have just called them 0s, right? Because I said that this should be called 0. So let me call this 0. And then all of these 2's should be called 1s. So this is a 1, 1, 1, 1. And this is a 1, right? And these are 2s. So I've labeled all of the depths. And now we can find a numbering quite easily. Maybe I'll use red for that. Certainly, this could be chosen as a 1, as the first one, right? And it would be safe to choose all of these, let's say 2, 3, 4, 5. Choose all of the depth 0 ones first, right? And now let's choose all of the depth 1, 5, 6, 7, 8, 9, 10. And then we'll choose all of the depth 2, 11, 12. And we could continue if we had more. Okay? And it turns out that if we use this procedure to number, we could get better partitions. Okay, it kind of means that if we have a node that has really high depth, okay, we have a node that has a really high depth. We don't really want to number this node earlier on, because if we did, then there could be all of these additional edges that are created because this is a really long path, and in the transitive closure, all of these additional edges would be created. So we kind of want to add nodes in order of increasing depth. Want to add nodes in order of increasing depth for the partition inverse algorithm. So in this example over here, this is a triangular matrix. Did we number the nodes according to depth? Actually, let's see. So 1, this has depth 0. 2, this has depth 1, but it was immediately numbered. So in other words, in this example, we numbered nodes not according to increasing depth. The matrix is still triangular, right, because all of the arrows point from lower to higher. But this heuristic was not satisfied. Okay? So this is a potential improvement, okay, over the naive algorithm for doing this. And of course, I should say again, you can't always find such a numbering, such a permutation. Okay, so exercise for tomorrow, very simple, is to take this numbering that we have in red over here and to find the partitions. And the interesting question is whether or not the number of partitions is smaller than for this graph. So exercise for tomorrow, find the partitions for the reordered L, in other words, for the LQ, of the example. So that's this example here. Okay? Any final questions? Okay, if not, have a good evening, and I'll see you tomorrow.